Dear friends, this lecture is devoted to chi-square test. This is one of the most known tests in sociology. When we interview sociology students for admission in graduate programs and we ask, do you know any statistics? They always tell that they know correlation and they know chi-square. But actually there is very little understanding of chi-square test, its assumptions, its applications, interpretations and limitations. And this lecture is devoted to all these aspects of chi-square. When is chi-square used, how is it interpreted, how is it used as a measure of strength of association, and how is it used in hypothesis testing, and we will also discuss limitations of chi-square along with certain examples. So, chi-square is used for measuring strength of association between two attributes, say A and B. Just now I said that there are categories of A and categories of B, A1, A2, A3 in rows and B1, B2, B3 in columns. Chi-square is used for measuring strength, to what extent categories of A affect categories of B. Chi-square is also used for testing hypotheses regarding independence of two attributes, which means whether belongingness to any category of B, B1, B2, B3 depends on belongingness to categories of A, A1, A2, A3. Now, like normal distribution or other distributions, the probability density function of chi-square calculated from sample data will also have a probability density function. Anything which is calculated on the basis of sample data fluctuates from sample to sample, and therefore, it is subjected to sampling fluctuations and it has a probability density function. It is a family of distribution. Why? Because like Poisson distribution is a family of distribution with one parameter lambda, chi-square also has a parameter and which is called degrees of freedom k. Chi-square is a family of distribution with degrees of freedom k, and it varies from 0 to infinity. It cannot take a negative value. If you ever find that your chi-square is negative, just check the calculations again, because chi-square means square of something and square of negative numbers is also a positive number. Chi-square is also used for comparing observed and expected frequencies. Expected frequencies will come when you assume a model of relationship between things, or an independent model like a regression model or factor analytic model or some other model. It may be a pure mathematical deterministic model, or it may be a statistical model involving stochastic processes and error term. It tests goodness of fit of theoretical model then chi-square is also used for testing goodness of fit of any model. The first bullet shows that it compares observed and expected frequencies. Expected frequencies will come under some model, whether when you apply a model, what will be your expected frequencies according to that model, if the model is valid. So, for by comparing observed frequencies in your empirical data and expected frequencies which will come by assuming that a given mathematical or statistical model is adequate to represent the data, you test goodness of fit of the model. Chi-square is also used for structural equation models or advanced factor analytic models for comparing something called say covariance matrix and correlation matrix. Covariance matrix which is shown by the data, and covariance matrix which will be shown if the model assumed is confirmed. So, that the general formula for chi-square is that chi-square is sigma of an expression. What is that expression? O minus E. O stands for observed frequencies, E stands for expected frequencies when you assume that some model is correct, and O minus E square divided by E. It is chi square is sum of this. Chi square is sum of O minus E whole square divided by E. Here degrees of freedom of chi square is n, number of categories which you are comparing, minus 1 minus m, where m is the number of parameters of the model which are estimated from the data itself. An example, in an experiment a coin is tossed 4 times and the distribution of number of heads is obtained. This experiment is performed suppose 50 times and the results are as shown in the table. This is the table. Now, if a coin is tossed 4 times, you may get no head, 1 head, 2 heads, 3 heads or 4 heads. There are 5 possibilities, and by doing this experiment 50 times, you find that 0 appeared twice, 1 appeared 10 times, 2 appeared 20 times, 3 appeared 10 times and 4 appeared 8 times. This is how we calculate chi square. Mean number of heads is 2.24, n is 4. So, if we assume that this distribution 0 to 4 follows a binomial distribution. In binomial distribution the parameters are like p. You calculate p from these data. In binomial distribution theoretically mean of a distribution is n into p, n is 4 and p is to be calculated. So, p of the binomial distribution whose n mean is n p would be this mean 2.24 divided by n or 4 or 0.56. Now, you write a model that NCR p raised to power r, q raised to power n minus r and obtain theoretical probabilities of getting 0 head, 1 head, 2 heads, 3 heads, 4 heads if the probability of getting a head is 0.56. Expected frequencies are probabilities multiplied by total number of cases observed. So, if probability of getting 0 head is 0.037, expected frequency against 0 would be 0.037 multiplied by 50 or 1.85. Like this, expected frequencies for all values of x or all numbers of possible heads are calculated. They are for 1 9.5 to 18.2 etc. O minus E, these are O values, observed values, these are E values, you can calculate O minus E, 2 minus 1.85 equal to 0.15. O minus E square will be square of 0.15, this 0.0225, and O minus E square divided by E, this is E, is 0.012162. For each value of x you calculate O minus E whole square divided by E and add, the addition gives you 4.01. This 4.01 is the value of chi square. Now, whether this value of chi square is statistically significant or not means whether a value of chi square 4.01 is possible purely due to sampling fluctuations or it can be assigned some meaning, that depends on its comparison with tabulated value of chi square. For degrees of freedom 3, here degrees of freedom is calculated as there are 5 possibilities, 5 rows to be compared. So, 5 minus we have estimated 1 parameter p. So, minus 1 minus 1 or 3. Chi square value for 3 degrees of freedom and 0.05 value of p or alpha is 7.82. Now, since chi square calculated is 4.01, which is less than this, it means the null hypothesis that model is okay cannot be rejected. That means our model fits the empirical data well. These data show that the occurrence of head follows a binomial distribution with probability 0.56. As I said that like any other measure calculated on the basis of sample data, chi-square follows a probability distribution. Density function of chi-square is this. Normal everybody knows 1 upon sigma root 2 pi raised to power minus half x minus mu by sigma whole square. This is the density function of chi-square. F x equal to 1 upon 2 k by 2, where k is the degrees of freedom, gamma k by 2 x raised to power k by 2 minus 1 e raised to power minus x by 2. Shape of chi-square you can see from here. This is the shape of chi-square distribution. Chi-square goes from 0 to infinity. The distribution of chi-square is called the chi-square distribution obviously. The chi-square distribution with k degrees of freedom is the distribution of a sum of the squares of k independent standard normal random variables. It is determined by degrees of freedom. The simplest chi-square distribution is the square of a standard normal distribution. The chi-square distribution is used primarily in hypothesis testing. Actually, this O minus E square by E follows a standard normal distribution, and sum of this becomes a chi-square distribution. These are the shapes of chi-square distribution, which are derived from this probability density function. You see, you put values of k. If k is 2, then for k equal to 2, x raised to power 2 minus 1 is 0. So, that this term containing x vanishes, and when so it simply becomes a kind of negative exponential distribution. And what I want to say is that in that case, for k equal to 2, this is the shape of the distribution. This is the shape of the distribution. It starts from a certain point on y axis, goes down and then becomes asymptotic. For 3 or 4 degrees of freedom, it will be like this, green color, 4 degrees of freedom. And for higher degrees of freedom, as the value of k increases, for 6, 7, 8, 9, 10, 11 or higher degrees of freedom, chi-square acquires the shape of a normal distribution. Higher is the value of degrees of freedom, more close chi-square distribution is to a normal distribution. If you may ask, what if k is 1? Yeah, for k equal to 1, it will look like the chi-square distribution for k equal to 2, but in that case it will never touch the y axis, it will be asymptotic to y axis. While for k equal to 2, it starts from certain point in the y axis. For k equal to 1, it will never touch the y axis. Chi-square for contingency table is a special case of goodness of fit. As chi-square is used for testing goodness of fit, actually in contingency table also we are testing goodness of fit. Goodness of fit of what? It is of the hypothesis that the two attributes B and A are independent of each other. Belongingness to B is not dependent on belongingness to A. So, under the assumption that two attributes are independent, we can calculate expected frequencies for all the cells using this null hypothesis that the two attributes are independent. Alternative hypothesis would be that B depends on A or A depends on B, means they are not independent. If null hypothesis is rejected, it means that A and B are not independent, but whether B depends on A or A depends on B, that cannot be said on the basis of chi-square. Direction of relationship cannot be determined. This only will tell you whether A and B are independent or they are not independent, they are dependent on each other. We also assume that marginal totals and grand total are fixed. So, under the assumption that A and B are independent, we calculate observed frequencies, and for each cell O minus E square divided by E will follow a normal distribution, standard normal distribution, and sum of O minus E square by E for all the cells will follow a chi-square distribution. Here is an example that we have data from a large sample 7,710, and these 7,710 people are divided according to two attributes, two qualitative variables. One is non-migrant, short distance migrant, long distance migrant, and total. That means, according to migration status of respondents, whether they are non-migrant, they are natives, or they are short distance migrant, or they are long distance migrants. These categories are categories according to education. For example, this number 698 is the number of respondents who are illiterate. Out of the 7710, 698 respondents are illiterate and they have moved only short distance. If you want to calculate probabilities of respondents belonging to one particular category, then you divide cell frequencies by grand total. Now, the probability that out of this population of 7710, a randomly selected person belongs to the category of non-migrants would be this. The probability of the respondent being part of short distance migrants will be this, long distance migrants will be this. Similarly, if you predict only one characteristic like education, then the probability that a randomly selected person would be illiterate is this, literate is this, primary is this, and high school and above is this. Some other category the person will belong to, and therefore, sum of these three probabilities as well as sum of these four probabilities will be 1. Now, imagine the cell HS. HS means high school and above. High school, probability that the respondent is high school, this is the probability, 753 out of 7710 belong to high school. Similarly, probability of long distance migrant will be 0.07, this is 0.07, probability of belonging to high school is this 0.9, and probability of belonging to long distance migrant is 0.7. So, 0.7. Now, if the two attributes are independent, if education and migration status are independent, then the probability of belonging to two categories, high school and long distance migrants, will be multiplication of these two probabilities. This will be 0.010376. Empirically or observed frequency is 80. Okay. Observed frequency is 80 for this category. Expected frequency would be this 0.1. Expected frequency will be obtained by multiplying probability of HS and probability of LDM multiplied by 7710. In this way, we will calculate 7710 and product of these two numbers will be 007 and 55.8. Now, see the difference. The difference between 55.8 and 80 arises because if the null hypothesis is correct, if education and migration are independent, then we expect that in the category of this high school and LDM, long distance migration, there must be 55.8 if the null hypothesis is correct. That if education and migration status are independent of each other, then we will expect, this is our expectation, we will expect that there will be 55.8 persons in this cell of HS and LDM. But actually in the category of HS and LDM, you have 80 people, there is a difference. That means according to comparison in this particular cell, our null hypothesis may not be true. There is a difference of 80 minus 55.8 equal to 24.2. Similarly, for all the cells, we can compare actual frequency with expected frequency. For expected frequency, we have to calculate probability of that, probability of belonging to that cell, and that probability comes from multiplication of probabilities according to two attributes separately, and then we calculate O minus E whole square by E. We can say that the contribution of this cell to chi square is 10.495, because 10.495 is O minus E square by E for this particular category HSS and LDM. So, the contribution of this cell to chi square is 10. We can calculate such contributions for all the cells of the contingency table and add. By adding all of them, we get chi square for the contingency table. And degrees of freedom is obtained by k equal to r minus 1 into c minus 1. Here r is the number of rows, c is the number of columns. And this chi square can be taken to be the measure of association between two attributes, and this can also be used for testing the hypothesis that the two attributes are independent of each other. For sample data, if chi square calculated is greater than chi square tabulated for alpha equal to 0.05 or p equal to 0.05, then we reject the null hypothesis. Otherwise, if calculated value is less than the tabulated value of chi square according to probability density function of chi square for p equal to 0.05, then we reject the null hypothesis that if chi square calculated is greater than chi square tabulated, means for probability density function of chi square with k equal to this r minus 1 c minus 1 given degrees of freedom, then we reject the null hypothesis. But if the calculated value of chi square is less than the tabulated value of chi square, then we do not reject the null hypothesis and we say that the two attributes are independent. Chi square for contingency can be used for multivariate tables also, means when imagine that the 7710 number was cross classified according to three attributes: gender, males, females, education and migration. Then chi square can be used for testing independence pairwise and also overall. But then expected frequency should be estimated more carefully. The multiplicative rule of probability will apply, like the probability that somebody will show a particular category of gender, a particular category of education and a particular category of migration will be probability of A into probability of B into probability of C. And in that case, students of sociology who have very little knowledge of statistics often calculate expected frequency as row total divided by grand total into column total, or row total into column total divided by grand total. Somehow everybody remember this, that for any cell, how to calculate expected frequency, take the row total multiplied by column total and divide by grand total. This rule is okay for for a contingency table with 2 attributes, but if you have multiple attributes 3 or more, then you have to be more careful, and the expected frequency cannot be calculated as row total multiplied by column total divided by grand total. Then you have to go to basics and use this probability for A, B, C, and this multiplied by the sample size or population size will give you the value of expected frequency for a particular cell of A, B, C. In Sydney and Siegel's book, it has been shown that chi-square can be subdivided, and one can know from which categories of A, B, C or from which categories of A and B greater contribution to chi-square comes. It is not necessary that dependence of A and B are spread over all the categories of A and B. Maybe there are some categories from which more significant contribution to overall chi-square comes, and that can be done. Chi-square can be subdivided according to degrees of freedom, and you can know from which specific categories of A and B a contribution, significant contribution to chi-square comes. Here is again an example of use of chi-square. There are 2 categories of A, A1 and A2. There are 2 categories of B, B1 and B2, and these are the data. The total sample size is 300, out of which 200 belong to B1, 100 belong to B2, and 100 belong to A1, 200 belong to A2, and these are the observed frequencies in 4 different cells. Like there are 60 cases who belong to A1 category according to A and B1 category according to B. Then we calculate expected frequencies. This is a case of 2 attributes. So, we can calculate expected frequency as row total multiplied by column total divided by grand total. So, this category A1 B1 will have an expected frequency this 66.7 is obtained by multiplying 200 row total by 100 100 means column total, this is row total, this is column total for A1 B1 and divided by 300 or grand total. So, 200 multiplied by 100 divided by 300, this is 66.7. 66.7 is the expected frequency for this cell. Similarly, for this cell it is 100 multiplied by 200 divided by 300, that will be the expected frequency in this cell, which comes out to be 66.7. 66.7 differs by 60 by 6.7, and here 66.7 differs by 60 again by 6.7. The difference is same. That is because of the nature of these data and classification according to A and B. In all the cases, differences may differ. Then we calculate chi-square. There are 4 cells A1 B1, A1 B2, A2 B1, A2 B2. These are observed frequency, these are expected frequencies. The difference is this, a square of differences is this. See that if you simply observe O minus E, suppose you add O minus E, you will always get 0. That is why chi-square is designed that way, that we square O minus E. There will be some negative differences, some positive differences, and addition of all the differences will give you 0. So, we take O minus E square, and then O minus E square is divided here I should mention this is O minus E square divided by E. So, 44.89 divided by 67.7, this is what 0.6730 is. 1.34 is 44.89 divided by 33.3, like that. When you add them, you get 3.03. So, calculated value of chi-square is 3.03. Add divided by E here.
which is missing. Tabulated value of chi square for degrees of freedom, how many? R minus 1 will be 1, there are 2 rows, C minus 1 will also be 1, there are 2 columns. So, degrees of freedom will be 1 into 1 equal to 1, and for 1 degree of freedom and p equal to 0.05, value of chi square is 3.84. So, your calculated value of chi square 3.03 is less than the tabulated value. This means that your null hypothesis can be true and calculated value of chi square can go up to 3.84. So, since calculated value is less than this, so null hypothesis of independence between two attributes cannot be rejected, and that means A and B seem to be independent. This is how we interpret chi square. There are some limitations of chi square. Chi square cannot be used indiscriminately in all cases. First of all, remember, as I mentioned right in the beginning, that chi square is used for frequency data only. You cannot use chi square for actual values or numeric data. Another limitation of chi square is that chi square will be used only when no expected frequency should be too small. No expected frequency should be too small. Now, there are differences in opinion regarding what is too small. Some people will say that an expected frequency less than 5 will be too small. Some will say expected frequency of less than 1 will be too small. Some will say that whether we go for 5 or 1, it depends on number of categories and sample size. But anyway, expected frequencies should not be too small. If some expected frequencies in some cells are too small, it will be better to merge the categories of A or B and ensure that all the expected frequencies are more than 5. Now, another limitation which I have written in red is that chi square depends on sample size or grand total. It is very serious problem, which means if the pattern of relationship, means probabilities of belonging to different categories of A, different categories of B, or jointly to different cells or different categories of A and B are same, but the pattern emerges from a larger sample. Same, you may have the same pattern, but in one case sample size is less, in another case sample size is more. Then chi square for that sample which is of higher size will be higher. Imagine that one sample is of size n, another sample is of size 2n. Then the chi square for the sample of size 2n, despite similarity of pattern of distribution of frequencies, will be double the chi square for n. Chi square for 2n will be double the chi square for n. So, that means chi square in itself cannot be interpreted, because chi square not only depends on the nature of relationship, whether relationship exists or not, how strong is this, but it also depends on sample size. This is a problem with chi square. So, no interpretation of direction or relationship or order, as in the case of correlation, can be given to chi square. It depends, chi square value depends on the arrangement of contingency table. If you merge 2 or more categories, your value of chi square will change. If you change the rows or columns, then chi square will change. That means, a particular value of chi square is typical of a particular arrangement of the contingency table. If some other researcher uses other categories of A or other categories of B or other categories of both, his chi square for the same data would be different. For interpretation, it needs to be compared with chi square for appropriate degrees of freedom, and whether a particular value of chi square is statistically significant or not cannot be said just by looking at the value of chi-square. You have to compare your chi-square with tabulated value of chi-square, and the tabulated value of chi-square comes from observing values of chi-square for different levels of alpha or type 1 error for a given degrees of freedom. Degrees of freedom is the parameter of the chi-square distribution. Other alternatives. What are other alternatives if data are cross classified according to two attributes or two polytomies? In case some assumptions of chi-square are not satisfied, say there are several expected frequencies which are less than 5 or less than 1, and you do not want to merge categories. In that case, Fisher's exact probability test can be used. This Fisher's exact probability test is part of non-parametric statistics, and it calculates exact probability of getting a particular configuration or a contingency table, keeping marginal totals and grand totals fixed. Fisher suggested this test, and therefore, this is called Fisher's exact probability test. So, here we use logic like calculate the exact probability of getting a particular configuration, a particular contingency table for a given sample size, keeping marginal totals fixed, and then make it more extreme, make your contingency table more extreme, again calculate exact probability, make it still more extreme like that, and then calculate the value of alpha for a contingency table. So, you directly calculate exact probability of getting that contingency table or a more extreme contingency table, and you can decide to whether to reject the null hypothesis or not reject the null hypothesis by calculating this exact probability of getting the configuration or a more extreme configuration. Other alternative is long back, maybe in 1950s, Goodman and Truskell made a detailed critique of chi-square distribution. They found several problems in chi-square. With the same data and with the same classification, you can get different values of chi-square, and some chi-squares will be significant, some chi-squares will be insignificant. They looked for impact of sample size on chi-square, impact of direction change, whether A affects B, B affects A. Chi-square cannot be used to say whether A affects B or B affects A. Change of categorization and several other things, and made a detailed critique of chi-square test. And they suggested a lambda, another test. This lambda is based on an interesting logic. The logic is that imagine that between A and B, you are asked to predict values or the right category of B. Just you predict the right category of B. What you will do? You will take that category which has the maximum frequency. Now, you can calculate probability that a randomly selected person belongs to that category, the category of guess. You will also involve some probability of committing error in guessing that, which will be 1 minus probability of belongingness to that error. Now, imagine that you know the other category, you are guessing B, and now you are given that the person belongs to A1 category of A. Okay. Then also you make the best guess. Then the best guess of B may not be the same category of B which you were guessing in absence of knowledge of A. In both the cases, you can calculate how much error, relative error you make in predicting values of B. It is an abstract issue. So, let me repeat. Imagine that there are two situations. In one situation, you are asked to guess the right category of B for a randomly selected person. You may say it is B1 or B2 or B3 or B4, which will depend in which category of B you have the maximum number of cases. You do not know anything about A. So, you can calculate probability of your being right in guessing that category of B. Then you are told that as far as A, that there is another characteristic of the person, and that is A, and you are told that the person belongs to this category of A. It is like in the empirical case just now we saw relationship between education and migration. You may ask a question regarding what is the best guess about migration status, and then in the second case you are told that the person is illiterate. Now guess the category of migration. In both the cases you will make some error, some error in predicting the right category of migration, and the relative difference in the prediction of migration without knowledge of education and with knowledge of education, that is defined as a kind of lambda. There are two lambdas. One, you may be asked to guess migration with or without knowledge of education, or you may be asked to guess educational category with or without knowledge of migration. In both the cases there will be some reduction, relative reduction in error probability, and therefore, there are two lambdas, lambda in predicting B, lambda in predicting A, then there is an overall lambda also. By utilizing this concept, whether knowledge of one characteristic helps the researcher in predicting other characteristic, that is at the root of this proposal of lambda by Goodman and Kruskal. Two lambdas, one for B, another lambda for A, and then an overall lambda. They are called lambda B, lambda A, and overall lambda. So, this is an alternative to chi-square. Then there are other alternatives to chi-square. Some alternatives are based on information theory and measures of entropy and redundancy. This entropy is a function of P log P. P is the probability of belongingness to some category and log P is log of P. By using probabilities of belongingness to different cells in a contingency table and taking their log and adding them, you can arrive at some measure of entropy. Normally in sociology we do not use such concepts, they are only of theoretical interest. So, I am not discussing them, but if somebody is interested in alternative measures based on chi-square, alternative measures other than chi-square, then one can look for Goodman and Kruskal's lambda and information theory based measures entropy and redundancy. In addition to qualitative analysis, chi-square is also used for comparing covariance and correlation matrices. We will talk about correlation matrix in case of factor analysis. Basically it means arrangement of correlations between variables taken pairwise. A structural equation model is often proposed by empirical researchers showing the various linkages between observed measures, variables and latent factors or constructs discovered from data. Covariance correlation matrices constitute the inputs in these models, and once a model is developed, you can calculate covariance and correlation matrix for the model, that if model is true, what kind of correlation matrix will be obtained. And by comparing empirically observed data and the correlation matrix that you have got from the data with correlation matrix or covariance matrix which will arise if your model is correct. You can check whether your model is okay or not, and this comparison is done based on chi-square statistic. Covariance matrices are compared by using chi-square. One can also compare correlation matrix with identity matrix to establish that different variables share some relationship. In simple sociological applications, chi-square is used if you have data on two attributes. Sample data are cross classified according to these attributes. The nature of data is frequency data, calculate chi-square, fix alpha and compare the calculated value of chi-square with tabulated value. If calculated value is less, do not reject the null hypothesis of independence. If it is more, reject the null hypothesis. And then if the null hypothesis is rejected, identify categories which are basically responsible for dependence. Rejection of hypothesis of independence depends on alpha and on sample size, because I said that chi-square depends on sample size. Now, what is alpha? This is alpha. For this chi-square distribution, we fix a critical region. Normally, this critical region is fixed at 0.05 or 0.01. This is the value of chi-square beyond which alpha or p value or probability of rejection lies. If your calculated value lies in critical region, means calculated value is more than this value of chi-square beyond which 5% or 1% area lies, then you reject the null hypothesis, and if your calculated chi-square is less than this value, means it is in this region, then you accept the null hypothesis. I think you have some basic idea of chi-square. Basically, for you a simple application is in testing goodness of hypothesis that the two attributes according to which your data are cross classified, or you have a contingency table, whether that hypothesis is okay or that model or hypothesis is okay or not. Thank you.